Welcome to the first lesson in the new unit, which is called Thermochemistry and Thermodynamics. In this lesson, we're going to talk about heat energy and specific heat. And we learned about specific heat in honors chemistry, and we also learned a little bit about it in AP Bio when we were talking about water. So you have actually mostly learned all of this lesson at some point. Okay, so first of all, heat and temperature are not the same thing. Okay, temperature is a measure of the average kinetic energy of the particles, which is a measure of really how fast the particles are moving. Remember, the higher the temperature, the higher the particles on average are moving. And if remember, we saw that Boltzmann curve, which shows sort of like the number of particles at each speed when the temperature is changed. Okay, and it measures the hotness and coldness of an object, and it also tells us the direction in which heat will flow. Like osmosis and diffusion, heat always flows from an area of high heat to an area of low heat. Okay? And as you know, it's measured in Celsius, Kelvin, and Fahrenheit. Now, heat is the exchange of thermal energy, which is caused by a temperature difference. And like I said, heat always moves from areas of high temperature to areas of low temperature. Okay? So it's the amount of energy being transferred, or thermal energy being transferred. Okay? And it can only be measured when heat is being transferred from a hot object to a cold object. And if you know, we measure heat in two units that you've heard of. We measure heat in joules. And you could also, it's also measured in calories. So for example, the energy in your food is measured in calories, and that is calculated by burning the food and seeing how much energy is released. And we're actually going to do that in a lab on Tuesday. So to summarize, temperature is a measure of the average kinetic energy of the particles, or really how fast the particles are moving. And heat is the type of energy that's used to change temperature. So to make the molecules move faster, or if you remove heat, to make the molecules move slower. We're going to look at an example of this looking at a block, so the difference between temperature and heat looking at a block. So here we have two blocks. We have an aluminum block, which has at 99 degrees Celsius, and you have 20 grams. And we have another aluminum block, which is at 100 degrees Celsius and has 10 grams. So when we're looking at temperature, which block is hotter, we simply look at the value of the temperature. And since the smaller block has a higher temperature, okay, it is hotter. Okay. However, if we have the same blocks, and we ask which one contains more heat energy, okay, in this case, the bigger block contains more heat energy. While the temperature of this block is 1 degree lower, it's double the size, okay? So it took twice the amount of heat to get it to 99 degrees. It would take twice the amount of heat to get it to 100 degrees than it would to get it to, not if it was the same. So to get it to 100 would take more heat. So there's more heat stored in this block than this, because it's bigger, even though the temperature is lower. So here we have the same two blocks here. And the question is being asked, in which direction would the heat flow in order to reach thermal equilibrium? Okay? And thermal equilibrium is reached when the temperature is done, when the heat is done flowing. And the rule that's applied here is that heat always flows from the hot temperature to the cold temperature. So in this case, we try to find the temperature that's hotter, and 100 degrees block is hotter than that. So the heat is going to flow from the small block to the big block. Okay, so now we're going to talk a little bit about thermal equilibrium. So let's say you have equal quantities of hot and cold water in an insulated container, which is called a calorimeter, which we're going to deal with on Tuesday. And it wants to know what the final temperature of the mixture will be at thermal equilibrium. Okay? Now, this is assuming that no heat is lost to the air. Okay? And that's why we're using an insulated container, which is a very big assumption that we're going to talk about on Monday. So, but if you mix equal quantities of hot and cold water, okay, the heat from the hot water is going to move into the heat from the cold water until the temperature, okay, is in between the two temperatures of the hot and cold water. Okay, now, here's a different example, okay? What's different about this example is that we don't have equal masses. So we're mixing 50 grams of cold water at 20 degrees Celsius with more 75 grams of hot water at 80 degrees Celsius, okay? And the question wants to know, what will the final temperature be at thermal equilibrium when all the heat has been transferred, okay? And the thing here is that since there is more, in this case, hot water, okay, than cold water, when the heat is done flowing, when thermal equilibrium has been reached, okay, the temperature, because there's more hot water, okay, is going to be closer to the hot water temperature. Okay, now, this is very different from what we learned, like, in osmosis and diffusion, when, like, the molarities are always equal. So, it's not true with thermal equilibrium. It does not always have to be the middle temperature. Okay, and we're going to see another example of this later. But because there's more hot water, when you mix those two together, okay, the final temperature, the temperature at thermal equilibrium, is going to be closer, okay, to the hotter water temperature. Now we're going to look at one more situation where we're changing the liquid in one of the cups. So here we're mixing 50 grams of alcohol at 20 degrees Celsius with 50 grams of hot water at 80 degrees Celsius. So the amounts are the same, okay, but the substance is different, okay? And using this information, okay, we would not be able to tell, okay, the final temperature would be closer to the alcohol or closer to the hot water, okay? And the reason why that is that different substances gain and lose heat at different rates. We're going to relook at the math of this question on Monday because the math's a little complicated. But today we're going to talk about what it means or why substances gain and lose heat at different rates. Okay? And that idea is based on something called specific heat. Okay? And it's this we learned, and you've seen this equation before. Okay? And specific heat is the quantity of heat or the amount of heat that is needed to change 1 gram of the substance and raise its temperature by 1 degree. Okay? Now if we look at the specific heat of water, okay, the specific heat of water is 4.18, and the specific heat of ethanol is 2.46, and the AP exam tends to use specific heat capacity, which really means the same thing. Okay, now what does this mean? Okay, so since water has a higher specific heat, okay, it takes more heat to heat it up than ethanol. Okay, so if you wanted to heat these two, if they were started at the same temperature, and you had the same amount of them, okay, and you wanted to heat them, and get them to the same temperature, it would take more heat to heat water than it would take to heat ethanol. Okay. It also goes the reverse, right? If you wanted to cool this down, right, it would have to lose more heat to cool down, okay, than ethanol would have. Another example of this, and I've talked about this in Honors Chem, like if you have a pot on a stove, the pot has sort of two parts, the metal part and sort of like the plastic handle. The plastic handle doesn't heat up as fast as the metal because the plastic handle has a higher specific heat than the metal of the pot. Okay, now this is the equation. Okay, and so the equation is Q equals MC change in T, which we did, and it's important to see that the change in T is equal to the final temperature minus the initial temperature. C is specific heat. M is mass in grams, and Q is heat in joules, or the energy transferred in joules. We are going to look at some problems. I'm going to stop this video and upload it, and then we're going to look at 5 problems, which you guys have done this, that you can do with this equation. Okay, so this is just, you need to get this concept, all right? So, an object that has a high specific heat, okay, will take, than another object, let's say, will take longer, or you need to add more heat to raise its temperature. Similarly, it will also take longer, okay, or more heat needs to be released to lower its temperature. So here's an example. So let's say you're going camping and there's a campfire and you're cold, okay, and so you heat up both a jug of water and a rock and they're of equal mass, and you heat them up both to 43, and then you're ready to go to bed and you want to bring it into your bed with you because you're cold. Okay, I don't know why, but so now, the question is, which one would keep you warmer? Okay? And just to let you know, water has a higher specific heat than the rock. Okay, so since they're both at the same temperature, 43 degrees, it took more heat, okay, for the water to get to 43 degrees Celsius than it did the big rock. So as a result, there's more heat in the water than the rock, okay? So the water will be able to release more heat through the night and also release it slower, okay, than the big rock would, which has a lower specific heat, okay? I would hope that you would either, like, pause this and play it back and write this down here. Like, circle the water, circle the big rock, and write down what I just said. Alright, I'm going to upload this, and then we're going to do some problems with this. The next video should only be about 6 minutes long, or 7 minutes long. So you should be done. Alright,